Okay, so you want to understand how a company makes a fortune off a phone that costs a fraction of its selling price to actually build. Design a sleek slab of glass and metal, put a fruit logo on the back, charge $1,000 for it, and watch people line up around the block to buy one on the very first day it goes on sale. That's the picture in your head. Look at the number that gets thrown around every single year when a new phone launches. Some analyst breaking down the bill of materials and announcing that the phone costs maybe $400 or $500 to build, sold for $1,000, and you think that's an obscene, almost cartoonish profit margin on every single unit, the kind of gap that seems to demand an explanation all on its own. Here's the problem. You are looking at a number that measures almost nothing about how this business actually works, and the real economics of manufacturing a smartphone at global scale are buried in places that number never touches at all. The truth is that a company like this is not really in the business of manufacturing phones in the way people imagine it. It is in the business of designing, financing, and orchestrating one of the most complex, most tightly coordinated global supply chains ever built by a private company. One where the actual assembly of the device is almost the least interesting part of the entire operation. And once you understand that, everything about why this remains one of the most profitable products in the history of consumer electronics, and why almost no competitor can replicate the margin even when they copy the design, starts to make sense. Let's start with what that bill of materials number actually means, and more importantly, what it deliberately leaves out. When you see a headline claiming a phone costs around $450 to build, that figure is measuring the cost of the physical components: the display, the processor chip, the camera modules, the memory, the battery, the aluminum or titanium frame, added up at the price the company pays its suppliers for each individual part. It is a real number, and it is genuinely useful for understanding component-level economics. But it excludes almost entirely the cost of research and development that went into designing those components in the first place. The cost of the custom manufacturing equipment built specifically to produce them at the required scale and precision. The cost of software engineering for the operating system running on the device, the cost of the retail stores and staff selling the phone, the cost of marketing campaigns launching it, the cost of customer support handling it for years afterward, and the cost of warranty service and returns. A bill of materials number is a snapshot of raw parts sitting on a table. It is not a picture of the actual cost of bringing a phone from a blank sheet of paper to a functioning global product line shipping tens of millions of units within the first few weeks of release. Now here's where the naive mental model starts to break down in a more specific way. You think the expensive part is the physical assembly, screwing the components together inside a factory. It isn't, not remotely, and this is genuinely counterintuitive. Final assembly, the actual process of putting a finished phone together from completed components, is one of the cheapest parts of the entire manufacturing chain, largely because it has been deliberately engineered to be cheap through decades of process refinement and, historically, through labor cost arbitrage, locating final assembly in regions where manufacturing labor costs significantly less than it would in the country where the company is headquartered. The real cost and the real competitive advantage that's genuinely difficult for a rival company to replicate sits one or two layers upstream from final assembly, in the manufacturing of the components themselves. Take the camera system as one example among many. A modern flagship smartphone camera isn't a simple lens and sensor bolted together. It requires specialized optical engineering, precision-manufactured lens elements stacked in exact alignment measured in microns, custom image sensors fabricated in dedicated semiconductor facilities, and computational photography chips designed specifically to process that visual data in real time. Building the factory capacity capable of producing these components at the volume and precision required, tens of millions of units per year with extraordinarily tight quality tolerances, requires capital investment that can run into the billions of dollars. Investment that has to be committed years before a single finished phone ever reaches a retail shelf, based on demand projections for a product that, at the time the investment decision gets made, doesn't exist yet in any finished form. This brings us to a financing mechanism that almost nobody outside the electronics industry understands, and it's arguably the single most important structural advantage a company at this scale actually has. Rather than building and owning every piece of specialized manufacturing equipment itself, a major smartphone maker will frequently prepay suppliers enormous sums of money specifically earmarked to build out dedicated production capacity, sometimes running into the billions of dollars for a single component category, in exchange for guaranteed priority access to that capacity once it comes online, often locking in preferential pricing for years into the future as part of the same agreement. This is a genuinely brilliant piece of financial engineering when you look closely at it, one that few outside the industry ever hear discussed in this level of detail. The smartphone company doesn't have to carry the specialized manufacturing equipment as a depreciating asset on its own balance sheet. The supplier, who now has guaranteed demand locked in for years, is willing to take on the debt and build the factory because the risk of that capacity sitting idle and unprofitable has been dramatically reduced by the guaranteed order volume. This arrangement effectively lets the smartphone company access manufacturing capacity worth many billions of dollars while keeping a meaningful portion of that capital cost off its own books. A structural advantage that a smaller competitor, unable to guarantee anywhere near the same order volume, simply cannot negotiate for itself on remotely comparable terms. There's a layer of cost buried even further upstream than the component suppliers themselves, one that almost never shows up in any bill of materials breakdown at all. The raw material sourcing that has to happen before a single chip or battery cell can even be manufactured. A modern smartphone contains dozens of different minerals and rare earth elements, materials used in everything from the vibration motor to the camera's optical image stabilization system to the battery's core chemistry. Many of these materials are concentrated in a small number of mining regions globally, and the supply chains connecting a mine to a refined, purified material suitable for electronics manufacturing are themselves long, complex, and often subject to significant price volatility driven by factors having nothing to do with the smartphone industry at all. Everything from electric vehicle battery demand competing for the same lithium and cobalt supply to geopolitical export restrictions on specific rare earth elements that a handful of countries effectively control the global refining capacity for. Smartphone makers increasingly sign long-term supply agreements directly with mining and refining companies, sometimes even prepaying for future material allocation years in advance, essentially applying the same financing logic used with component manufacturers one layer further back in the supply chain, because losing access to even one obscure but essential mineral can halt production of a specific component entirely, with no readily available substitute material capable of matching the exact same performance characteristics. Now let's talk about where these components and this assembly actually happen, because the geography of this supply chain is itself a massive part of the economics. A modern smartphone's components are sourced from suppliers spread across a dozen or more countries. Semiconductors from one region, display panels from another, camera modules from a third, memory chips from a fourth, each shipped to a small number of massive final assembly facilities, historically concentrated heavily in East Asia, where hundreds of thousands of workers at a single campus can assemble, test, and package finished devices at a scale and speed that would be extraordinarily difficult to replicate almost anywhere else on Earth. These assembly campuses aren't simply large factories, they're essentially self-contained small cities, with dormitories, cafeterias, and medical facilities on site, built specifically to support a workforce that can scale up dramatically in the weeks before a major product launch and scale back down afterward. A flexibility in labor deployment that would be genuinely difficult and expensive to replicate in a labor market with different regulatory and logistical characteristics. In recent years, largely driven by geopolitical tension and a strategic desire to reduce concentration risk in a single country, smartphone makers have been actively diversifying a portion of final assembly to additional countries, building new assembly capacity in South Asia and elsewhere. This diversification comes at a real measurable cost. Building an entirely new assembly ecosystem, training a new workforce, establishing new supplier relationships with local component providers, and navigating a different regulatory and logistical environment. All of that takes years and requires substantial upfront investment, and even once that new capacity comes online, it frequently operates at a somewhat lower efficiency than the decades-refined ecosystem it's supplementing, at least for the first several years of operation, which quietly increases the effective per-unit cost of every phone assembled at the newer, less mature facility during that transition period. Now, the assembly process itself, because there's a genuine engineering story here that the simple bill of materials number completely ignores. Assembling a modern smartphone involves hundreds of individual steps, precision robotic placement of components too small and too delicate for reliable manual handling, adhesive application requiring exact timing and pressure to avoid damaging waterproofing seals, screw torque calibrated to a precision that would strip the threads if applied even slightly too aggressively, and a testing and quality control process at the end of the line rigorous enough to catch defects invisible to casual inspection. A single assembly line producing a specific phone model can represent tens of millions of dollars in specialized tooling and equipment, custom built specifically for that model's exact dimensions and component layout, equipment that becomes essentially worthless the moment that specific model gets discontinued and a new one begins production, because the physical tolerances are simply too tight to repurpose the same equipment for a meaningfully different design. Here's the part that actually explains the extraordinary profit margin, and it isn't primarily about underpaying anyone for physical labor, even though labor cost arbitrage plays a real role. It's about scale, and specifically about a concept economists call amortization of fixed costs across an enormous volume. The billions of dollars spent designing the custom processor chip, developing the camera system, engineering the software, and building out specialized manufacturing capacity are what's called fixed costs, expenses that don't meaningfully change whether the company sells 10 million units or 200 million units of a given model. When you spread several billion dollars of fixed development cost across 200 million units sold globally, the fixed cost burden per individual unit becomes remarkably small, often just a few dollars per phone once you divide it out across that kind of volume. A smaller competitor building a broadly comparable phone, but selling only 5 or 10 million units instead of 200 million, is spreading that exact same category of fixed development cost across a dramatically smaller number of units, meaning the fixed cost burden per phone for that smaller competitor can be many multiples higher, even if their component bill of materials looks nearly identical on paper. This is the real moat. More than the brand, more than the retail experience, more than the software ecosystem, though all of those matter too. Scale itself becomes a self-reinforcing competitive advantage. Higher unit volume means suppliers compete harder for the business, driving down component prices through sheer negotiating leverage that a smaller buyer simply doesn't have access to. Higher unit volume means fixed development costs get amortized across more units, lowering the effective cost per phone. Higher unit volume means the company can justify prepaying suppliers billions of dollars to build dedicated capacity, which a smaller competitor placing a fraction of the order volume could never credibly justify or finance on comparable terms. Each of these advantages reinforces the others, and the gap between the market leader's effective per-unit economics and a smaller competitor's economics tends to widen over time rather than narrow, even when the smaller competitor is using genuinely comparable component technology sourced from many of the same underlying suppliers. Now, the pricing side of this equation, because the retail price isn't simply cost plus a fixed markup, it's calibrated against a completely different logic entirely. The company isn't pricing the phone primarily against its own cost structure. It's pricing against what the market will bear, positioning the device at the top of a category where a meaningful segment of consumers have demonstrated repeatedly and across many product cycles a willingness to pay a significant premium for brand, ecosystem lock-in, resale value, and perceived status, independent of how that premium compares to the underlying component cost. This is why storage tier upgrades, moving from the base storage configuration to the next tier up, are priced at a markup that can be many multiples higher than what the actual additional memory chips cost the company to source. Because that pricing isn't really about the marginal cost of a few additional memory chips at all. It's about capturing consumer willingness to pay for a meaningfully differentiated product tier, a pricing lever with essentially pure profit margin attached to it, once you understand that the underlying component cost difference is genuinely small. There's a second engine running quietly alongside the hardware margin that deserves genuine attention, because it changes the entire long-term profitability calculation in a way the initial sale price alone doesn't capture. Once a phone is sold, it becomes a platform for years of recurring revenue that has essentially nothing to do with manufacturing at all. Subscription services, App Store commission fees taken from every transaction that happens inside third-party applications, cloud storage subscriptions, and extended warranty or insurance products sold at the point of purchase. This services revenue category tends to carry gross margins dramatically higher than hardware itself, often exceeding 70%, because the marginal cost of serving one additional subscriber or processing one additional App Store transaction is extremely small compared to the revenue it generates. This is a meaningful part of why the company is willing to accept a thinner effective margin on the hardware sale itself in certain competitive situations, because the phone functions, in a very real financial sense, as the entry point into a multi-year services relationship that ultimately generates a substantial share of total company profit over that device's lifetime, a dynamic that fundamentally changes the calculation from what looks like a single transaction into what's actually the beginning of a long-term revenue relationship. The trade-in and resale ecosystem plays a similarly underappreciated role. A smartphone maker that actively promotes trading in an old device toward the purchase of a new one isn't simply offering a customer-friendly discount. It's securing a steady stream of used devices that get refurbished and resold into secondary markets, often in regions where the original new device price point is out of reach for a large share of the population, extending the effective revenue lifetime of a single manufactured unit well beyond its original owner and creating an entirely separate profit stream on top of the original sale, one built on components and manufacturing investment that have already been fully paid for once. Let's talk about what can go wrong in this business, because even at this scale, the model has real vulnerabilities. There's also a regulatory and reputational cost that has grown meaningfully in recent years, tied to how repairable and how long-lasting these devices actually are. As phones have become more tightly integrated, batteries adhered rather than easily removable, components soldered directly to the main board rather than modular and swappable, independent repair has become significantly harder, and regulators in multiple regions have responded with right-to-repair legislation requiring manufacturers to make parts, tools, and repair documentation more widely available to consumers and independent repair shops rather than funneling every repair through the manufacturer's own service network. Complying with this legislation carries real costs, establishing new parts distribution channels, publishing detailed repair documentation that was previously kept entirely internal, and in some cases redesigning future products to be more modular specifically to meet regulatory requirements, all of which represents a genuine tension against the manufacturing efficiency and precision that comes from tightly integrated, purpose-built assembly in the first place. There's also a concentration risk sitting underneath this entire supply chain that's arguably even more serious. A significant portion of component supply for critical parts, particularly advanced semiconductors, is concentrated in a remarkably small number of specialized manufacturing facilities globally. Facilities that require such extraordinary capital investment and manufacturing precision that only a handful of companies on Earth are even capable of operating them at the leading edge. This concentration creates a genuine single point of failure risk. A natural disaster, a geopolitical conflict, or even a routine equipment malfunction at one of these highly concentrated facilities can meaningfully disrupt global smartphone production for months, because there simply isn't a readily available alternative supplier capable of stepping in at the same precision and volume on short notice. During a global chip shortage several years ago, driven by a combination of pandemic-related demand shifts and semiconductor manufacturing capacity constraints, smartphone makers across the entire industry were forced to redesign products on the fly, substituting alternative components where possible and, in some cases, delaying product launches entirely. A reminder that even the most sophisticated and well-financed supply chain in the world remains genuinely vulnerable to a handful of extraordinarily concentrated choke points that no amount of financial engineering can fully insure against. There's a real case study worth walking through here, because it illustrates exactly how concentrated this risk actually is in practice. Several years ago, a fire at a single semiconductor supplier's specialized manufacturing plant, a facility responsible for producing a specific type of chip used across a huge share of the global electronics industry, including smartphones, caused measurable ripple effects across component pricing and availability for months afterward, even though the fire itself was contained relatively quickly and didn't affect the majority of that supplier's overall production capacity. The incident demonstrated something important, that even a partial, temporary disruption at a single facility, one representing a small fraction of global semiconductor capacity overall, can meaningfully affect pricing and availability industry-wide, because the alternative capacity simply doesn't exist in sufficient volume to absorb the shortfall on short notice. Smartphone makers responded by further diversifying supplier relationships where technically possible and building larger safety stock inventories for the most critical, hardest-to-substitute components, a response that itself represents a real, ongoing cost, capital tied up in inventory sitting in a warehouse specifically as insurance against a disruption that may or may not ever actually happen again. So how does this business actually make money in plain mechanical terms once you strip away all of this complexity? The core engine looks like this. Retail price minus component cost, minus amortized fixed development and tooling cost per unit, minus assembly and logistics cost, minus retail and marketing cost, equals gross profit per phone. If a flagship phone sells for $1,000 with a component cost of around $450, an amortized fixed cost burden of perhaps $50 to $75 per unit at high production volume, and assembly, logistics, retail, and marketing costs adding up to another $100 or so, the company can be left with a gross margin in the range of $350 to $400 per unit. A genuinely extraordinary margin by the standards of almost any physical manufactured product, and one that becomes possible specifically because of the volume this particular company is able to move. Here's the volatility that comes right alongside that math. Component costs for things like memory chips and display panels can swing significantly based on global supply and demand cycles in those specific component markets, cycles the smartphone maker doesn't control and can only partially hedge against through long-term supply agreements. Currency fluctuations affect the relative cost of manufacturing in one region versus another, and a single quarter of weaker than expected demand for a specific model, if it's significant enough, can leave the company holding excess component inventory purchased under a long-term agreement at a price that no longer reflects current market conditions. A real cost that shows up quietly on the balance sheet rather than as a single dramatic headline event. Let's put together the two versions of a single product cycle, because this is where the real picture shows itself. In the optimistic scenario, a new flagship model launches to strong demand, sells well beyond the volume needed to fully amortize its fixed development and tooling costs within the first year. Component costs for key parts like memory and displays stay stable or even decline slightly due to favorable industry-wide supply conditions, and the company's negotiating leverage with suppliers, built on that enormous order volume, secures favorable pricing that a smaller competitor simply cannot access. Under those conditions, gross margins on that specific model can run comfortably above 40%, translating into extraordinary total profit once multiplied across 200 million units sold globally. In the realistic scenario, a new model launches to merely solid rather than exceptional demand, meaning fixed development costs get amortized across a somewhat smaller unit volume than originally projected. A component shortage in one category forces the company to pay premium spot market prices for a portion of its supply rather than the favorable long-term contracted rate, and a stronger local currency in a key manufacturing region quietly increases assembly costs for that product cycle. Under those conditions, gross margin on that specific model can compress by several percentage points compared to the optimistic case, a difference that sounds modest as a percentage but translates into billions of dollars in aggregate profit difference once applied across the full volume of units sold globally that year. The difference between those two outcomes for the exact same phone, built with nearly identical components, can run into billions of dollars in aggregate profit across a single product cycle, and almost none of it shows up as one dramatic headline event on launch day. It's a slightly less favorable memory chip contract here, a slightly weaker currency exchange rate there, a component shortage forcing a slightly more expensive substitute part in one specific region, compounding quietly across 200 million units until the number in the annual earnings report looks meaningfully different from what the enthusiastic launch day reviews and the lines outside the retail store on release morning would have suggested to anyone standing outside watching them form. The phone in the customer's hand is identical either way. The packaging looks the same. The keynote presentation covered the exact same features. None of the difference between the good product cycle and the difficult one lives in anything a customer unboxing their new phone could ever actually perceive, because it was never really happening at the retail counter in the first place. It was happening years earlier, in a supplier negotiation room, a mineral refining contract, and a factory financing agreement that most customers will never hear about at all. So if you ever find yourself trying to understand how a phone that costs $450 in raw parts sells for $1,000 and generates one of the largest profit pools in the history of consumer electronics, remember the one thing that actually explains it.
It was never really about the parts inside the box. It's about being the only company on Earth capable of ordering 200 million of those boxes at once and building an entire global supply chain, one strategic financing decision at a time, specifically designed around the fact that nobody else can.